Okay, so now let's do some examples. Um, so for more examples, um, watch lecture, previous lecture from week 11, and also watch Adrian's office hour from Friday, from last Friday. Okay, so let's do one more example here, and that will be it. Okay, so evaluate the principal value. Let me write here of the following integral: cosine x and right x squared plus 1 and x squared plus 9. Okay, so let's do this. First, we have to turn this. So yeah, first we turn it into a complex integral. Okay, so let's do that first. We use that e to the ix. Let me write it this way: cosine of x is equal to the real part of e to the ix. This is just Euler's formula. Okay, so let me do this so you can see it. Okay, so now, um, okay, so we're gonna study the integral e to the I z, z squared plus 1, z squared plus 9, dz. And what is that? This is the integral from minus r to r of this guy f, but f of x. Let me write it. It's fine. EIX. And then the line integral of this function. Okay, so we're looking at this guy. All right, uh, fine. So yeah, always try to do the easy stuff first. So um, let's apply the lemma because in this case there's not much to do. So let's show that the CRF goes to 0. Let's do that. That's easy. So from our lemma, from Jordan lemma, let me write this right. From the Jordan lemma, we set P to be PZ to be 1, and so degree n is 0, and we set Q of z to be z squared plus 1 and z squared plus 9, and so degree m is 4. Okay, and therefore we have m is bigger than n. Okay, so Jordan lemma applies, and we get the zero integral in the limit goes to 0 as you take the radius to infinity. Okay, so that guy's out. So that means we're left with the integral c and the limit of this of our guy plus 0. Okay, so this guy is what we want, right? This is the principal value. That's how we defined it. Um, After we take the real part. So it would be the real part PV of what we want. So we will do this at the end. Uh, all we have to do now is do residue theorem. So as always, first step, find, so let me call it second step. Okay, so you can have an algorithm. So now second step, find the poles. Okay, in order to apply residue theorem. All right, so we have z squared plus 1, and you factor this guy to this, and you have z squared plus 9. So you factor it in this way. So we have plus minus I plus minus 3i. All right, let's go back to our picture. This guy is here, 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 and here. So only, let me do them in color. So we have only two poles are inside, I and 3i. Is that okay? All right. And their order is 1, as you can see from here. The exponent is 1 of order 1. Okay, so that's it. Let's do residue theorem. So we have 2 pi I residue of the function at I order 1 plus residue of the function 3i also order 1. Okay, and there's not much to do. So what you do, you have the function times f of z evaluated at z equal I, and plus z minus 3i f evaluate at z equal 3i. Okay, good. Now, so f was this guy, right? Z squared plus 1, z squared plus 9i. Sorry, plus 9. Okay, so, right. So I did all the computation, and you get what is it here? Yeah, 2 pi I, and then the first guy gives you e to the minus 1 2i8, and the second guy e to the minus 3 minus 8 18i. So these are the two residues, and then you just put them together. So pi over 8, pi over 8 e inverse e2 minus 3 9. Okay, so what's the punchline here? Yeah, let's see. Okay, so what do we have? We had principal value EIX, and then x squared plus 1 x squared plus 9 dx is equal to the, call this f, f of z. Let me write it for you so you see everything together. So this is EIZ, z squared plus 1, z squared plus 9. Let me add the 0 as well. Remember, we we killed it by Jordan's lemma. Uh, and then this is equal to this guy over here. Call it star. Okay. All right. So we're almost there. Now I just take real parts. Take real parts. And left hand side becomes cosine x squared plus 1, x squared plus 9 dx. And the right hand side doesn't change. So it's pi over 8 e inverse 3/9 because it's already real. And that's the final answer. Okay.